This video was produced by
Thanks very much, Daniel, and thanks to David as well for the invitation to speak here today. And it's lovely to see some, familiar and friendly faces, and also not so familiar but also friendly faces too. So today I'm going to talk about a very old book, possibly the oldest book of, possibly the oldest kind of coherent text, for want of a better description, in mathematics. And I'm going to talk about this particular. I'm going to talk about this very old book in the context of this also old book, but not as old, only dating from 1847 as opposed to ancient Greece. I want to start off maybe just by talking a little bit about what we mean by mathematical proof with an accessible example involving a 7-year-old, and then from there, then we'll talk about will that be a kind of a springboard into Euclid, and we'll get to see lots of nice pictures as well. Okay, so I'm going to start off with a story about it was my daughter's 7th birthday, and we're in the car. I think we're coming back from swimming, and I was asking her about her school bus, and she said she was telling me about the ins and outs of the school bus, and then we got onto this. You can get tickets if you're bold, if you're out of line on the school bus, and the more tickets you accumulate, the more trouble you get into. So I asked my daughter, I'm like, did you ever get a ticket? And she was completely indignant, like taken aback, like, no, absolutely not. How dare you, And I was like, no, I didn't mean it, I said, there could have been some misunderstanding or, so then I was like, completely tongue-tied. And I'm like, well, who gets the tickets then so? And she says, oh yeah, I need to change his name because this is being recorded. She said, what name did I use again? Bob. Yeah. Bob gets all the tickets, right? So then at this point, I'm like, Bob, so like, what kinds of things, does Bob do? Well, he stands up and he should be sitting down and, he should be following the rules and he should be doing what safety patrol tells him. I'm like, oh, very interesting. I'm like, what age, is this Bob? And at this point, I stopped and I was like, well, so like the people who ride the bus are like in kindergarten to 5th grade. And so what age do you think Bob was? 5th grade, right? Very reasonable inference, right? One would even describe it as, good intuition, right? So you'd start from there, but you're not certain, right? So you'd say maybe he's in 4th grade. Maybe, but 5th grade is maybe, the likely. He's got an open door. So 5th grade is, is the likely thing. But then, what my daughter said was she gave me what's effectively, a mathematical proof. She said, well, my friend Alice told me that he's in 5th grade. And I'm like, well, how do you know this? She goes, well, Alice's sister is in the same class as Bob. Alice's sister is in 5th grade. So Bob has to be in 5th grade. Needless to say, I was just, I nearly swerved, off the road, with excitement, right? 7 being like the traditional, age of reason. And like, it was like, her 7th birthday. And I was like, this is just great, right? So of course, what do I have to do is, I have to take this very cute story about, my daughter's, wonderful thinking and turn it into some dry formulaic mathematical theory, which is what I'm about to do now, right? So let's come up with an axiomatic framework for Bob the young bus delinquent, right? So there are a few things that my daughter didn't state, right? She says, the first axiom is in some sense, right, a person is trustworthy unless proven otherwise, right? So, that's not like a provable statement. It's more a way of being, in the world, right? What kind of world do you want to live in? An axiom is kind of like a social contract. And you're allowed to have social contracts in mathematics as well. You're allowed to say, lines, circles, we care about. I'm allowed to do these kinds of things with lines. Yes, that's my social contract, right? And you're allowed to have more than one axiom as well. So the first proposition is that my daughter, her friend Alice, and Alice's sister are trustworthy. And the proof is that we really have no reason to think otherwise. We have no evidence to the contrary. Right? And then proposition 2, you would say Bob the delinquent is in 5th grade. And you would say by proposition 1, Alice's sister knows and is truthful about who is in the same class as her. And also, again, by proposition 1, Alice also knows who is truthful and about what grade her sister is in. Bob is in the same class as Alice's sister, and so must be in the 5th grade. Right? So here, right, your structure is like, you're trying to boil down to your, what are the essential axioms or assumptions that are at stake? You could just, so kind of, state this very clearly. You could assume that everybody just tells the truth, but that's not a very good social contract, right? I think we all know better than that, right? And then we have, a proposition. We have this kind of preliminary proposition, and then here's my daughter's argument, right? Implicitly referring this kind of axiom here in place and this previous proposition. All right. So now, we write this argument in mathematics because, one reason is that it's kind of the model that we've had for so long, and it's a very successful model, coming from ancient Greece, coming from a text called Euclid's Elements. And in the same way, it kind of develops, a collection of axioms. It describes lines, circles, and triangles. These are the things that we care about. And we can do certain things with lines, circles, and triangles. I'd say a little bit more about that. Things that are in Euclid's Elements are the Pythagorean Theorem, the fact that pi is a constant. That's a proven statement that you can deduce from a collection of simple axioms. The Pythagorean Theorem is also a wonderfully rich statement, but that again, if you work really hard, 48 propositions to be precise, you get to the Pythagorean Theorem from this very simple collection of axioms that you slowly kind of build up and develop, right? So the title of the talk is Seeing Believing in Geometry. And one of the wonderful tensions that plays out in Euclid is that you really want to trust your eyes. You want to trust what's happening with your eyes, but you also want to verify things as well. So this is why you're so careful with spelling out the axiomatics, right? So reasons to maybe not trust your eyes is that, with your eyes, it would look like the rails of train tracks meet. All right? That's one maybe reason to be skeptical of what happens, with your eyes. And, maybe a more central one to Euclid is, how do you look at two fields and measure where, and determine whether they're the same area or not? Let's even not say the same area, but like within a 1/16th of an acre, from each other. That's a really hard thing to do. There's only so much that one's eyes can do. So you should trust your eyes, but also, follow that trust up, with a verification. I really like this expression a lot because it comes from an old Russian proverb that Ronald Reagan, during the close of the Cold War, used a lot with reference to the Russians. So he used their own proverb as a way of talking about, the disarmament of nuclear stockpiles. Trust the Russians, but verify that they've done what they've claimed. So anyway. So this tradition goes back, a long way. Plato, in the original, mathematical filter, said, let none ignorant of geometry enter into Plato's academy. Spinoza aims to understand human emotions as, and this is the quote, as if the surfaces of lines, planes, or solids. So if you look at Spinoza's ethics, I must confess I have not read it in full. So I'm doing a bit of, I read the review and I read papers about it, but I haven't read it in full. It's on my reading list. But Spinoza's ethics seeks to take this kind of Euclidean model and base a model of ethics on it, right? Lists a collection of axioms, tries to list out the logical conclusions then of these axioms, right? Kant also has a similar model. If you look at metaphysics, he spells out a similar model with the categorical imperative. You've got the three versions of the categorical imperative, and Kant kind of tries to look at the logical closures, of these statements, right? This is a quote here from Kant. This is from the other one, Critique of Pure Reason. Kant says, the absolute universality, which are characteristic of all propositions of geometry. So Kant is really a believer here in Euclid and refers to it frequently. So all this to say, Euclid is pivotal to ancient and classical education. Okay. So now let's talk a little bit more than so about what these axioms are in Euclid. So very simple things. There are 5, so-called, Euclidean postulates. It's just kind of a nice way, kind of, traditionally it is said that the postulates are kind of like the axioms about geometric things. So these are the 5 things that you're allowed to do. So if somebody gives you 2 points, you're allowed to draw a straight line between those 2 points. That's the first postulate. The second one says if somebody gives you a black line, right, the color is not important. I just want to refer to it here. If somebody gives you a black line, you can extend it as far as you wish. These are the so-called straight edge constructions, right? Namely, you could place a straight edge upon 2 points, or you could place it upon a straight line and draw accordingly on the straight edge. Postulate 3 says that if somebody gives you a line segment, like this one here in black, you can draw a circle with center at one extremity of the line, and then the radius of that circle is the length of the line segment itself. That's not exactly the way Euclid says it, but that's what it's saying. So this is the use, of the compass. So you might have heard the terms straight edge and compass construction. This is what these constructions are referring to. And then the last 2 are just kind of things that are saying, look, if I have any 2 right angles, right? These things you would have called, 90 degrees, in high school, maybe right angles as well. If I have any 2 right angles, I'm going to consider them to be equal, right? And then the 5th postulate, is a mouthful, which is indicative of it might be troublesome, and indeed it is, right? But here's what it's saying. It's saying that if you have 2 black lines, these black lines will meet if whenever you take a third line, namely the blue line, and you cross the blue line across the black lines in whatever position you wish, straight line going across, if the sum of these 2 angles is less than 2 right angles, then not only will the lines meet, but they'll meet on the same side as those angles. That's a mouthful, right? So for 2,000 years, I shouldn't say continuously, because there was a period called the Dark Ages where I imagine there was maybe 5 people in the world thought about Euclid. That's not a researched figure. I'm just I just want to be clear on that, right? But for many years, right, the big goal of studying geometry was that people were suspicious of this 5th postulate and said, well, can I find a way to deduce the 5th postulate just by combining the other 4 and whatever the logical conclusions are of the other 4? And that turns out to be false. I'll say more about that later. But that didn't occur until, the 1820s. Part of the reason why Kant back here was so excited, was such a believer in this kind of, the absolute universality of all propositions in geometry, was that the thinking for a long time was, as Sahiri would have said, is that Euclid is cleared of every flaw. Euclid is without flaw. Now, I should point out, this is, a common misconception about elements. Euclid never states that he believes that the 5th postulate must follow from the other 4. If you read the textual analysis, you'll see that Euclid is kind of postponing using the 5th postulate for as long as possible. But it doesn't mean that he thinks that, the 5th postulate, we just need to work harder and, it'll just follow from the other 4. Okay. So then, right, you have these 5 postulates in hand, and now I'm going to lose you for 2 minutes, but it has a point. I promise, okay? So now this is the first proposition in Euclid. So again, right, this is going to be a hard slog for 2 minutes, all right? So the proposition is to construct an equilateral triangle on a given finite straight line, right? So here it starts off and it says let AB be the given finite straight line. Okay, so what are you trying to do? You're trying to say let AB be the given finite straight line. And then it's saying, it's clarifying the proposition. So Euclid is in some sense, one of the great teachers actually, because he states a proposition in as much generality as he can. And then in the first paragraph, he always kind of explains what he's going to do, right? He always explains what he's going to do with reference to a picture. So let AB be the given straight line. And what you're required to do is construct upon AB an equilateral triangle, a triangle where all 3 sides are equal. And so then Euclid goes through the argument here very carefully in kind of long text, line by line, how this construction is made. And in most editions of Euclid, this is what the presentation looks like. Now, I'm not saying this is, a bad thing. I think one could read, say, Shakespeare and have the same sense, oh, the language is so awkward. But, I think there's much to be gotten from this difficult and challenging read. And even reading it in kind of, language that has, a lyrical quality that's perhaps different than, what you would be used to in these, modern times. So this was kind of the standard way in which Euclid would be presented. And then there was this book in 1847, and it talks about the same proposition, but uses colors and diagrams. Right? So this is the first proposition, same first proposition. Notice, first thing is the absence of letters. And also notice that there's no reference to, the absence of letters. And that all of the figures are colored. So here's what, and this is from Berns' edition of Euclid. It says, on a given finite straight line, this navy line here, it's kind of hard to see, this navy line, to describe an equilateral triangle. So you want to construct an equilateral triangle on this navy line, right? It goes on to say, notice the old-fashioned S's here, right? Describe this black circle upon this navy line. And also describe this red circle upon the same navy line, but here the center of the circle is the left extremity, and here it's the right extremity. And this is the navy and red circle respectively. And then it references, by the third postulate, I can do this. Right? Next it says, draw yellow or orange and red. Namely, draw orange here and red here. And kind of implicit is that you're joining it to the point at which these two circles cross. And then the claim, well, no, this triangle, navy, orange, red, will be equilateral. And now it just goes through the proof of this. It says, well, navy is equal to orange, and that's by definition 15. It's just saying that if you have, the circle, so here it's saying navy is equal to orange, so navy and orange are both radiuses of the same circle. And so by definition, they must be equal, right? And likewise for navy and red. And then finally, it's saying both this and this are equal to navy, so in fact, this and this must be equal to each other. And that's by another axiom that I didn't mention in Euclid that says two things equal to the same thing are equal to one another. Right? You might have seen that if you've watched Lincoln in the movie theater. When Lincoln is referring to Euclid, Lincoln talks about, two things that are equal to the same thing are equal to each other. And that's what this axiom 1 here is, right? Right? Okay. And therefore, this must be equal. So look at what the presentation is doing. It's really taking advantage of color. It's kind of not getting too caught up with the references to specific letters. And it's just really beautiful. The pictures are just stunning. Now, you might wonder why somebody didn't do this sooner, why we were stuck with these types of versions. I'm not saying these versions, are bad, but there is this kind of tension that somehow, if you spell things out visually, that you can't trust your eyes as much as you can trust, the cold logic here with sentences, lots of thuses, right, and since, etc., etc. So what this text, is attempting to do is to try and keep all of the mathematical rigor. The arguments here are exactly the same as the arguments here. Maybe some tiny things like, like this argument here would have said, let the point where the two circles cross, let that point be C. Right? Byrne here just kind of took that, well, you can just see where the point is, right? Didn't kind of explicitly say it, but it's not the kind of thing I'm going to lose sleep over. Okay. So that's the first construction. And again, you can see the themes, right? You're using the postulates that you've already assumed, right? You're just using, definitions then of things that you've already defined and axioms that you've already agreed upon as well. All right? So now this is another image. This is the construction of a regular pentagon, a non-trivial construction that takes some work to carry out. I just put it up there just because I think the picture is beautiful. But let's see what Berns says about, his version, of Euclid. And this is kind of Berns', manifesto, really, for want of a better description. Berns says most works addressed to people who are already proficient in mathematics, but not to the uninitiated. This is what he's trying to attempt to do with this color, right? He kind of feels that on some level somebody must be really skilled to be able to go through, an argument like this. And so instead, can we help people out with color? He says, he's trying to describe it as he would have explained it orally with his pupils. There's a nice nod back there to the, Socratic method, right? All things, in conversation, book being, a secondary form. He's trying to bridge this kind of gap between those two. And, he's a big fan of dyed chalks and colored pencils. He says they'll be very convenient, right? He says that they'll be very convenient. Let's look a little bit more at some of the things in Berns Euclid, if only to see the pictures. So the first thing, so this is maybe jumping a few propositions ahead, and it's about two triangles being equal. Well, any triangle has, I guess, a few characteristics, right? It has three sides and three angles. So then you might say, how can you tell if one triangle is equal to another? Well, certainly if all three sides and all three angles match up, then that's going to suffice. But you could also just have, well, this here is claiming, and here let's even just read through it. It says if two triangles have two sides of the one respectively equal to two sides of the other. So here, right, the color here is wonderful. It's saying, look, if red is equal to red and navy is equal to navy. And furthermore, if it's saying that these two angles are equal also to one another, then all of the, then the other remaining two sides must match up, the respective sides, and the two pairs of respective angles also have to match up. It's such a beautiful statement. Even if you didn't kind of go through the proof of this, it's very clear what the statement is, just from the spelling out of the proposition. So that's side-angled-side congruence. Here we've got isosceles triangles, and this just says that if you have the two red sides, if you have a triangle, ignore the bottom half of this. If you have a triangle and if the two red sides are equal, then the angles opposite them must also be equal. And he's kind of color coding once again. That's isosceles triangles. This is maybe one of my favorite proofs, and it really captures, the utility of Berns' kind of viewpoint on Euclid. And, let me just motivate this here, with some sticks. Can I have a volunteer? David, can I ask you, since you can't say no? Great stuff, all right, because you're, Yeah, okay. So now here, right, okay, so, hold the stick flat, all right? So here we've got three sides, okay? And I'm going to place each side at the bottom, right? And now here's the claim, right? These, if we have these three sides, and if they're fixed length, right, which they are, then this uniquely determines the triangle from which they come. So, another way of thinking about that is at this one point here where my finger and thumb are, this is the unique point where these two sides can touch, given that each side is attached to the respective, extremities, my left hand and David's right hand. Of course, that's not entirely true because we could turn them upside down, couldn't we? All right? We could turn them upside down. But it's just saying if you insist that the point is, on one given side, let's say this side here where my head is, then there is a unique point. Another way of saying that, thank you, David, thanks very much. Another way of saying that is if I give David these three sticks, and if I also gave Jason the same three sticks, right? And if I said to Jason, please make a triangle that uses the length of these sticks.
But he only had to hold one.
I know, I'm sorry. Here, look, I'll hold one, right? If I was to come over to, a different part of the room, and, the claim is that the triangle that I constructed with David is exactly the same as the one that I constructed with Jason. And that's all side is saying. It's saying if you have two triangles and the three respective sides match up with each other, then everything else about the triangles must be equal. This is not exactly what proposition 7 is saying, but very close to it. So this argument is really beautiful. It says, assume that there were 2 points. All right? So assume that, what myself and David were saying over here, or, what I was saying, that, there was more than one possible point, right? Well, if there were 2 points, then you would have the same stick, same red stick coming from this extremity, right? And the same navy stick coming from this extremity, right? And they would each meet, no problem, at these 2 points. Now, because this is an equilateral triangle here, then it means that this angle here, the red and black angle, must be equal to the navy angle. Right? So this whole one must be equal to this. Now, I know visually it's screaming at you, those are clearly not equal, right? Okay? But maybe that's just because, you've just drawn the picture, incorrectly. You want an argument regardless of what the length of your 2 red lines and your 2 navy lines would have been. Right? So, let's go along. Let's suppose this was equal to that. And then it says, okay, well, those would be equal if these 2 red lines could exist like so. Those would be equal. And now it's saying, well, the red angle is less than the navy angle. That's just because the red angle is a part of this big one here, isn't it? So the red angle must be... Did I say something wrong there? I did, didn't I? Oh, yeah. The red one is less than the navy one. But then the red one is also less than the navy and the... No, that's wrong now, isn't it?
That's right.
Oh, yes. The red one is less than the navy one. So the red one must be less than the sum of the navy and the yellow, because you've just made this angle bigger. But wait a second. This red angle, though, is equal to this one because of the second triangle. These 2 sides are equal to one another. And so it must be an isosceles triangle. So you get this very visual sense why you can't have these 2 points. It's because this angle would be equal to that one, and that one would be less than that one, and that one would be less than this one, but this one is equal to that one. So you get this kind of, tail, you get the snake, eating its tail kind of phenomenon. All right?
There's not going to be a quiz, right?
No. There will not be a quiz. Okay. So that's SSS. All right? So next, let's maybe talk about another example where you can't really trust your eyes, so to speak, right? So you might have seen before about the areas of parallelograms, that they're equal to the base times their perpendicular height, if you have a parallelogram. Well, one kind of nice way to see that is if you took the corner of one parallelogram and chopped it here, took this triangle and just kind of shifted it over. You could see then that, the color looked much better at home when I did this on the screen. This is supposed to be a gray chunk here, right? And clearly this is a rectangle, so it's base times height, but you've done nothing but move the area from one place to the other, right? You've picked up a triangle and you've moved it to, another place. That's all you've done. So, intuitively, it's pretty clear that the area of a parallelogram is its base times its perpendicular height because you can carry out this construction. Now, I'm not saying here to throw away your, intuition. But if you're just chopping things up, accordingly, it's not going to be enough. Because if you have some kind of a skewed parallelogram, again, same base and same height as this one, and if you carry out the same kind of chopping up again, you're going to move this triangle here to this, right? And now the area, it's not clear that this area here is just the base times the perpendicular height. You don't get to rely on the same, intuition here. I'm not advocating, that you, forget this. I'm just advocating that maybe we need to work, a little bit harder. That's all. So let's go through just very briefly the argument, in Euclid. So first of all, you take these 2 parallelograms and you kind of put one base on top of the other. All right? So, like so. And then you've got this parallelogram and this one. They've got the same base, same perpendicular height. And you want to show that this, like pink and purple, is equal to this purple and this, what color is that? Kind of bluish? Violet? Yeah, that'll do. Okay, all right. Pink, purple, and violet. Okay, great, right? So you want to show that pink and purple is the same as purple and violet. So you want to make this case, but without this kind of chopping up argument. And so what you could say is that you could say these two triangles, can you see the pink and white? You see pink and white? Pink and white together make one triangle. And then white and violet make one triangle also. Now, you're going to use some, SSS here, side, side, side. And you can show that this triangle and this one are equal to each other. So if you punch out this white region, you get pink and violet are also equal to one another in area. And then you can add purple to both. And that's exactly what you hope to show. Pink and purple is purple and violet. So that's kind of like, again, the Euclidean model, right? You've got lovely, intuition here, but sometimes, it only gets you so far. I guess the reason, why I'm showing this is that I don't want anybody to walk away thinking, oh, the intuition is enough. I can just kind of hold sticks together and chop things up, with the scissors. That there's really something special happening, with the Euclidean model. Okay. This is the argument, as Berns gives it, right? Right. It's, the exact same argument, and the picture is just beautiful as well. So, it carefully checks the triangle congruency condition, and then it's just kind of keeping track of the same addition and subtraction of equal areas. Okay. All right. I have to mention the Pythagorean Theorem, right? The Pythagorean Theorem is just a geometric statement, right? I'm not going to go through the proof here, but it's very similar to the area of the Parallelograms argument, actually, except that one's much easier to present, right? But here, right, what the Pythagorean Theorem is really saying, right? I know you're thinking about the arithmetic of a squared plus b squared equal to c squared, right? And fair enough, right? But what it's really saying is that if you have a right-angled triangle, if you construct a square of those side lengths on each of the sides, it's saying the area of this square plus the area of that square is equal to the area of this bigger square. And that's exactly what the Pythagorean theorem is saying. And the argument is very similar to what I just gave you for the areas of the parallelograms. All right? So all this to say, Euclid is kind of like this marriage of kind of visual comprehension and geometric rigor. And, the great success of Berns' edition is somehow kind of making this kind of gap kind of bringing it closer to one another. Much is made in mathematics about not depending on picture, but one person who was writing on Euclid and proof, Bill Castleman, made the very nice observation that says any proof you see of the Pythagorean theorem always has a picture. Almost always has a picture. So it's kind of, I think pictures are really important part of mathematical proof. I've certainly never seen a good one of the Pythagorean theorem without a picture. I guess you can construct one by a vector, analysis argument, but okay. Let's talk about what happened then to this great book. So, a few things. Well, it was published in, 1847. George Eliot's Daniel Deronda talks about one edition of Euclid's Elements as being like the sure thing for any second-hand bookseller. All right? If you could keep copies of Euclid on stock, you'll never go poor as a second-hand bookseller. So Euclid was very, well-read, or at least I should say well-bought. Well-bought. So what happened to Euclid in the Victorian era? So first of all, there was this, philosophical difficulty is that, with the emergence of non-Euclidean geometry, you could no longer talk about Euclid being cleared of every flaw, or Euclid was like the perfect model for the physical world. It just wasn't. The second kind of broad kind of sweep of things was this kind of, societal shift that kind of, viewed education, as, through the lens, of the liberal arts to one that viewed it through, a vocational training. And so there were a number of texts that came out at the same time, which were kind of, Euclid, but, from, the practical viewpoint. So I guess this would have just been after the Industrial Revolution. And one of the things that's kind of troubling is that, it was always assumed that artisans were only interested in direct, applications. That was one thing that was kind of surprising. Like this was always like, the underlying assumption of these different editions. So then you take something like, like Berns' edition of Euclid, and it's kind of, Euclid is, falling out of fashion, in some sense, because of the fifth postulate failing. This is a picture here of, what a non-Euclidean half-plane looks like. One way to think about it is that it's kind of like geometry, on a horse saddle, except on the boundary of that horse saddle, life gets very complicated. It's kind of, one way to think about it. And, I included this picture here because, one of my own favorite applications of the Pythagorean Theorem, I learned this working, on a building site once. Somebody wanted to measure if two planks, if two 2x4s were square to each other, were at a right angle. So they measured 12 inches in this direction, 12 inches in that direction, and then they tested that the distance between the two marks was 17. So that's like an almost Pythagorean theorem. 12 squared plus 12 squared is more or less 17 squared. So that was, I included this as like a practical aspect. So this is kind of like, the broader things that were happening, especially in Victorian England. And then Berns Euclid, in particular, here's a picture of Bern from, I think it's from the Library of Congress, actually. It's a steel plate. And that somehow, I say here that, Bern was caught between a technological rock and a traditional hard place. So one of the viewpoints for why one should read Euclid is that somehow you should read, remember the very first version we saw of Proposition 1? Like somehow this was like the real Euclid, right? Minimal dependency on pictures, and anybody worth their salt read the real Euclid, right? So Bern comes out, with this edition that, is very faithful to Euclid, but has lots of colors and, illustrations. And, the traditionalists are like, well, I'm not having this in my class, right? And then, the other, the rock, I suppose, the technological rock was that instead of this being a book that kind of talked about the practical uses, of Euclid, the color probably would have been very much embraced by ones who were, by folks who were promoting a practical viewpoint, of geometry. They saw this copy of Euclid and thought, well, this is just Euclid with, bells and whistles. There's still no practical applications. So Bern was kind of, like Bern could really please nobody, with either, with this edition. There was another prominent, there was a prominent mathematician. I shouldn't say another because Bern kind of just wasn't, as prominent for reasons that I don't know. But one of them is that, Augustus de Morgan, you might know De Morgan's laws from when you studied Venn diagrams or, things like that. You may or may not know. It's fine if you don't. But he dismissed Bern as an eccentric. And that in some circles was good enough to just dismiss Bern and his work. And then also money, right? As with all things. So the cost of this edition was 3 times more than the next most expensive version of Elements. So the great irony is that Bern wrote this for the uninitiated, right? Wrote it for, people who were not well-to-do and to give them access to this beautiful world of geometry, except that his book was just too expensive because the printing was so expensive as well. And in fact, the printing was so expensive that the publishers, Chiswick Press, they went bankrupt 6 years after publishing this. And you know what 75% of their stock was? This. On the point of money, I should say that these, not this version, this is a facsimile published by Taschen, 4 or 5 years ago. That's fine. This was a version published by Taschen, but if you get an original copy of this from 1847, it'll auction for $20,000. So If anybody finds a copy, let me know and we can go halves. So anyway, this was also a very, prohibitive. So these kind of three things, like a book that was fabulous but couldn't please the two main kind of forces behind the direction in which Euclid was going, it was in some sense doomed to failure. Bern was kind of bad-mouthed a little bit by this much more famous and prominent mathematician, and the money was also, a serious factor. So let me give a few references here. Daniel, I better know what's after happening. It's when you shut that screen, I'm betting. That's all right. Okay, here we go. All right. So not all the references. This will be available as well if you want to see more. I'll pass this around as well after the talk if anybody wants to look at it. This text here was especially helpful. It was my first time ever reading something from the Journal of Victorian Studies. It was a great read. It was really fabulous. I really enjoyed it. This current edition sells for like $55, but it's available free online. Just do a Google search for Berns Euclid, and there's like scanned copies come up. And then let me show you one last thing, a very kind of modern version, modern Euclidean pleasure. I'm going to come over here. Euclid the game. All right, and it's really something. It's great fun. I was surprised by how much I enjoyed this. It basically just goes through all these types of, Euclidean constructions. So here, right, this is just a tutorial to get you started, right? And it's saying, okay, it's asking you to draw a point from A to B. So I'm going to do that here. I'm going to use postulate 1. No, that's not what I meant. There we go, right? Well done, it tells me, right? And on I can go. But what it does is that it goes through all these various constructions that are present in Euclid, and it's just, anyway, it's better than solitaire. That's what I'd say. Okay, I'll leave it at that. I'll be here with this book if anybody wants to have a look or if anybody has any questions.